Geometry students, lots of vocab, lots of terms, and today you will be learning two different lessons in the book we're using, so going quickly through this chapter, but I think it's fairly straightforward. First, we're going to talk about what a perpendicular bisector is. Perpendicular bisector is a perpendicular line that bisects a segment, and a point is equidistant from two figures if the point is the same distance from each figure. Should make sense. So just a couple terms that you need to know, because our first theorem says if a point is on the perpendicular bisector, then it's equidistant from the endpoints, and then the converse is also true. If a point is equidistant from the endpoints, then it's on the perpendicular bisector. Pretty easy theorem to prove. Because it's a perpendicular bisector, I know this is a 90-degree angle. I know this is a right angle. I know this is a right angle. So I know those two right angles are congruent. It's congruent to itself, CP. We know this is the midpoint, so we know these two are congruent by the midpoint theorem. So I know these two triangles are congruent, so CPCTC says AC is congruent to BC. The reverse, I just use side, side, side. I know these two angles are, what am I trying to say? Linear pair. And they're congruent, so then I know they're both 90, so I can say they're both right angles, so I can say this is perpendicular. I knew this was congruent to itself. I had that. So, not too hard to prove that stuff. So, there you go. Anyway, we will use those theorems in the first lesson. This is where I think the interesting thing happens. Concurrency. This is Latin. Currency meaning running, and con meaning with, so running together, running with. If you draw the perpendicular bisectors of each side, so the perpendicular bisector here, PE, the perpendicular bisector DP, and the perpendicular bisector PF, turns out that all those perpendicular bisectors meet at a point called P, the point of concurrency, and that for perpendicular bisectors is called the circumcenter. What we know is, or what we can prove is, this point, any point on this perpendicular bisector is equidistant from B and C. Any point on this perpendicular bisector is equidistant from A and B. Any point here, equidistant from A and C. So this point right here, P, where they all meet, is the same distance from A, B, and C. And if you can draw a circle with that radius, it would hit all those points, and that is a terribly drawn circle. And that's what you can see down here. This point of concurrency of the three perpendicular bisectors of the sides of a triangle is called the circumcenter because it is the center of a circle that can be circumscribed about the triangle. Circumscribed comes from the Latin, circum meaning around, scribed meaning written. So written around the triangle, a circle that's written around the triangle. If it's an acute triangle, then that circumcenter is in the middle. If it's a right triangle, the circumcenter is actually the midpoint of the hypotenuse. And if it is a obtuse triangle, the circumcenter is actually outside the triangle. But that is called a point of concurrency. And there are 4 points of concurrency, and you just learned the first one. The next unit talks about angle bisectors. So notice that an angle bisector, we remember it's a ray that divides an angle into two congruent adjacent angles. Remember also that when we calculate distance from a point to a line, we use the length of the perpendicular segment. That's because on an angle bisector theorem, we know that any point on the angle bisector is equidistant from the sides of the angle. And the converse of the angle bisector theorem is if a point is equidistant from the sides of the angle, then it must be on the perpendicular, or it must be on the angle bisector. So now we're going to use that exact same theorem to talk about what happens when you have the three angle bisectors of a triangle. So angle bisector BP, angle bisector AP, angle bisector CP. They all meet at a point called P, which is the incenter. P is equidistant from side AB, from side BC, and side AC. It is actually the same distance from all three sides. So if you draw a circle with the radius right there, it would actually be inscribed in the circle. So inscribed means it's written inside the triangle. So a triangle can have an inscribed circle, which is drawn in, or a circumscribed circle, which is drawn around. Good? And that's pretty much it for this unit. It's just those theorems. And how are we going to use that? The big idea is when you know things are equidistant from sides, I can give you algebra problems. Or if you know things are equidistant from endpoints, I can give you algebra problems. Thinking about the proof of these theorems should be fairly easy to see. We know this angle is congruent to this. We know this side is congruent to itself. And then what else do we know? We know perpendicular. So we actually end up for this one saying we have two right triangles where the hypotenuse, we don't even need the hypotenuse leg, it's just angle, angle, side congruent to angle, angle, side. Over here we have this angle and we have this side and then we have this shared side. This one we do have to use hypotenuse leg. They share a hypotenuse. The legs are congruent. They're both right triangles. Therefore, the triangles are congruent by hypotenuse leg. So the angles here are congruent by CP/CTC. So that's an angle bisector. Remember, you can use that if and only if with these angle bisector theorems and the converse, right? So you can say a point is equidistant from both sides of an angle if and only if that point is on the angle bisector. It's kind of a nicer way to say it, in my opinion. So some things to practice there. There you go. Take a look at those again. We've got perpendicular bisector and the converse of that. We've got this idea of the circumcenter. That's one of your points of concurrency. Then we've got equidistant from the sides for the angle bisectors. And then we have the point of concurrency is the incenter. There's two more points of concurrency. You'll get those in the video due for Thursday. Have a great night. Peace.